Hey there, calc folks. Back here with another quick video where we're going to take a look at continuing our little discussion here on the precise definition of a limit. And we're going to look at the two cases now for infinite limits and limits at infinity. All right, we have to give ourselves some precise definition for these two scenarios. Along with these definitions, I'm also going to give you a couple of quick examples, folks, with these cases. So bear with me. Let's take a look at this. Let me bring this up. Try to make this video quick today. But the first definition we have to look at is for the case of an infinite limit. All right? And it's not called the epsilon delta definition. In this definition, we replace epsilon with the value of m. And instead of m playing the role of a boundary size like epsilon plays and like delta plays, m is going to play the role of a location. In this case, it's going to be a location found along the vertical axis, the dependent variable's axis. And it's going to be a location that we compare the dependent variable to in our calculation. It put together with the delta value in the epsilon delta definition of a limit, right, gives us the following understanding of an infinite limit. All right, here it is. Basically, to begin with, for a function y equals f of x, to be able to say that we have the infinite limit in the case where our function is heading off to positive infinity, notice this is case specific to this particular case, means for every location bigger than 0, right, there exists a corresponding delta greater than 0, boundary size around our value of a, such that the output of our function f at any value of x in the boundary around a is greater than that location along the vertical axis m whenever, right, our value of x is in this interval. Let's see if I can say that again a little bit more directly, right? In the m delta definition, you have a value of m that's greater than 0 and a corresponding value of delta that's greater than 0. Delta depends upon m, such that if we think about the absolute difference between x and a being less than delta, what we see is for any x in that interval formed by the size of delta around a, the value of f of x will be greater than the value, the dependent value of our function at x will be greater than the value of m. All right, that's called the m delta definition for a positive infinite limit. We also have the case for a negative infinite limit. Similarly, for the negative case, right, what that means is for every m, and I did kind of word this a little differently. I said, well, again, for every m greater than 0, there exists a corresponding delta greater than 0, such that f of x is less than that value of negative m whenever the absolute difference between x and a is less than delta. All right. I still went with m greater than 0 in this definition. I'm trying to see why that would be specific. Here's where the actual meat and bones is, right? We have the output of the function being less than the opposite of m with the requirement that it's greater than 0. I think we're just matching with above in this statement. But what we end up seeing is for any value of x in this interval around a with corresponding size delta, right, the output of our function f at that location of x will always be less than the opposite of m. Right? So it's called the m delta definitions for infinite limits. And I do have an illustration of this. Usually these definitions make a little bit more sense with an illustration. Here's the illustration of the m delta definition of a limit, where I should say of n, of a, we'll have to be specific here, maybe positive infinite limit. How do I spell that? The following illustrates the m delta definition of a positive infinite limit for a function. And what you notice in this illustration down here is that for every choice of x1 in this interval around a of size delta, it's going to produce an f at x1 that is bigger than the value of m. Where in this setup, for every single value of m we could possibly have as a location along that vertical axis bigger than 0, right? There is going to be this corresponding size boundary delta around a, where when we make the choice of x sub 1 in that boundary, we end up with an output of our function that's bigger than that value of m. Right? This is what the m delta definition is saying in its defining of the positive infinite limit. We would see a reflection of this scenario below the x-axis, across the x-axis, in the case for a negative infinite limit in this scenario. I don't have that illustrated, but you could imagine flipping this graph upside down, and that would be illustrating the negative case. That being a negative m in this situation versus a positive. That'd be the only difference. Right? F of x1 would then be below that negative value of m. Right? Let's look at a proof. Proofs are also pretty quick in the simpler cases. Here we have a case for a positive infinite limit. Consider proving the limit as x heads to 0 for 1 over x squared equal to positive infinity. Right? Well, what we need to show is for every m greater than 0, there is a corresponding value of delta greater than 0, such that when you take the absolute difference between 1 over x squared and 0, which is just going to be the absolute value of 1 over x squared, that is greater than the value of m whenever the absolute value of x, or x minus 0, is less than delta. All right? And where you begin these proofs is with, again, the m statement. And you attempt to manipulate that to obtain a statement on the left-hand side that resembles the delta statement, revealing to you how delta might relate to the value of m. If we consider this particular case, this is a quick solution. Right. What we would note is the absolute value of 1 over x squared being greater than m does imply that 1 over the absolute value of x would be greater than the square root of m. That I'd be able to take the square root of both sides, and because we're talking absolute value, it would just have to be the positive result for the square root of m on the right-hand side. Now, if I consider reciprocating both sides of that inequality so that the absolute value of x moves to the numerator, that will cause the square root of m to move to the denominator and the relationship in the inequality to switch its order, right? With the absolute value of x now becoming less than 1 over the square root of m. Now, what you might note is that is this statement right up here. This is equivalent to the absolute value of x in that statement being less than delta. And we can see how we might choose delta that corresponds to m. We might choose a delta that's equal to 1 over the square root of m. And that would be our choice in this example. Right? If we choose delta equal to 1 over the square root of m, we have a value of delta that corresponds to m, such that the absolute value of x equal to 1 over that square root of m ends up implying 1 over the absolute value of 1 over the square root, or the square of x, is always going to be greater than m. And how can we imply that? Well, we can work backwards through this algebra. We can take this statement, which implies this here, which can be said to imply this here, algebraically. Right? That is an illustration of the M delta definition. All right, let's take now a look at what's called the Epsilon-M definition for a limit at infinity. As you can see, again here, we're going to use this value of m in our definition. All right. But it's going to be used in place of delta as opposed to epsilon. Epsilon's still going to play that role of a boundary, but it, again, remember, is a boundary that's placed around, it's the size of boundary placed around the value of L that we hope to encounter f of x in, right? The output of our function at our value of x, right? And m now plays a corresponding value of the independent variable, well, or found in the region of the independent variable along the x-axis, right? It represents a location along the x-axis that's considered extremely large, right? That's kind of how m is playing the role. We use a capital M to kind of stand for maximum value, or a value of greatness, right? A large value, right? And what the definition says here is we can talk about a limit at positive infinity for f of x equaling L if for every epsilon greater than 0, there is a corresponding location along the x-axis that's bigger than 0, such that the absolute difference between f of x and L is going to be less than epsilon whenever x is greater than that location m along the x-axis. Right? In other words, we can say this is true, right? If there's a corresponding value of m that relates back to epsilon, where when I make the choice of x bigger than that value of m, the output of my function f of x is within that boundary of epsilon around L. It's called a limit at infinity. And this, like I said, these don't really, might not make as much sense until we kind of see an illustration. I also have similarly the case for a limit at negative infinity. Right? And here I do swap up the signs, or I don't swap up the signs with m, I swap up their order. I say there's a corresponding value of m less than 0, such that this is true. All right, take note of that in the definition here. Right? That m is less than 0 and you're looking for x being less than m. Now, if we want to kind of take in what all this means, here is the Epsilon-M definition for a limit at positive infinity. And what it says is for any size epsilon, for any size boundary that we put around the value of L, there will exist, and we can go back and see it here formed for this particular function, there will exist this boundary of m, right? That's greater than 0 along our horizontal axis here, such that for every choice of x1 that we make that's bigger than m, right? Here's a choice of x1 bigger than m. The output that it gives me on my function is within the boundaries that we place around the value of L, the boundary of size epsilon. Right? This is what the limit at positive infinity is illustrating. It's saying, yes, for every, no matter how big this size boundary is around L, I can find, using my function, a corresponding boundary of m, location of m, along the x-axis, where if I pick a value of x that's bigger, or in the case of negative infinity, smaller than that value of m, I'll always get an output of the function that's within those boundaries around L. It's called the Epsilon-M definition of a limit at infinity. Now, if we look at a quick example, we might look at 1 over x. Right? We know the limit as x heads to infinity for 1 over x equals 0. Right? So we need to show for every epsilon greater than 0, I can find an m greater than 0 that corresponds to it, such that 1 over x minus 0, the absolute difference there, which is just, if you take notice, is equal to the absolute value of 1 over x, right, would be less than epsilon whenever that value of x is greater than m. And again, where we start is with our epsilon statement, and we try to rewrite it into our m statement. And what we notice is 1 over the absolute value of 1 over x being less than epsilon begins by implying that the absolute value of x must be greater than 1 over epsilon. Right? And that pretty much gives us our value of delta right there. Or sorry, m, right? Let me not erase my work. So letting m equal 1 over epsilon, I can say there exists a corresponding value. I probably ought to make that note. Of m greater than 0 for every epsilon, such that the absolute value of x being greater than m, which equals 1 over epsilon, implies that 1 over the x's absolute value is less than epsilon. Right? How is it less than epsilon? Through this little link in the logic seen here in our preliminary work. This is called the Epsilon-M delta definition for a limit at infinity. All right. Again, I go back to, I present these just so that we can appreciate these definitions, folks. Do we need to know and have to prove each and every case we encounter? The idea there is no. But a very precise proof does exist for every single case that we can find, right? Or evaluate for every case we encounter. One of these proofs does exist in the background, supporting the result that you're finding through the techniques we discussed in class. All right. So I do not spend a lot of time on these because, again, I am just trying to give you a little bit of appreciation, at least for these last few examples. Right. But again, take note, you really don't need to prove every single case, right? And this is not how you go about evaluating limits. This is more a way of proving your final statement in the end as being true. Right? It's a little different than saying something like x plus 2 equals 5 and saying that's true when x is equal to 3. Because 3 plus 2 is equal to 5. That's a pretty quick proof that x would equal 3, right? However, to prove a limit statement is a little bit more involved. It involves this epsilon delta, or this m epsilon, or this delta m definition of a limit. I have that backwards. It would be epsilon m or m delta definition of a limit. All right. So I'll end there with this video, folks. Like I said, this was going to be a quick one, again, just to build some appreciation. And that does kind of wrap our study for limits, I do believe. I don't think I have anything else to add. If I did, I'd probably do that, go back to and add that at the end of a video specifically. But yeah, where we're heading is we're heading over into derivatives. We're going to start to look at our first application of a limit, big application of a limit. And that is developing a calculation in calculus known as the derivative calculation. And we're going to start a several chapter exploration into the derivatives. We're going to introduce the derivative and its calculations, and then we're going to look at application of it. Right? Which is really a good half a semester of Calc 1. All right. So we're just about to get into all that. All right. So hope you're out there studying. Keep studying, and I will be back with my next video to talk about derivatives, folks. And I'll see y'all then.